So today is going to be focused on practical stuff, examples of antennas, building antennas, but I want to make sure that everybody has, that we're all at least somewhat on the same page, that we have enough theory of like what's going on with antennas, how they're working, so that this all kind of makes sense. And I'm going to gloss through a bunch of this. So I want to be clear, this is not a PhD level class. This is going to be 20 or 30 minutes. So there's going to be some simplifying assumptions. There's going to be some lies we tell to children, right? Some very simplified explanations, and that is fine. We can, if somebody wants to dig in on something further, we can try that. But we do have a bunch to get to today. So what is electromagnetic radiation? What is radio? Basically, alternating current. You have some kind of generator. In this case, your radio, your transmitter, and it gets electrons swishing back and forth in some wires. Cool. Those go down your transmission line. For most of us, that's going to be coaxial cable, and they get to your antenna. You've got the two conductors in your coaxial line. They conduct to the two conductors in your basic dipole antenna. And now you get the electrons sloshing back and forth in the antenna itself. And that sets up, like ripples on a pond, that sets up electromagnetic waves that spread out through the universe forever. They just get weaker and weaker, expanding forever. That is your basic explanation of radio. Eventually, as those waves going through the universe, they will, somewhere else, encounter another antenna. And when those waves hit, they will get the electrons in that receiving antenna sloshing back and forth sympathetically. And that gets electrons sloshing back and forth in your transmission line, which gets to the receiving radio, and now you're talking. Your transmission lines, if all's going well, your transmission lines don't themselves radiate because the electrons sloshing back and forth in the two conductors in close proximity to each other, the fields cancel out, and that stays very well contained. So your transmission line not radiating, it gets out here to the antenna where it's just free to send ripples out to the universe. One thing I want to talk about here is on your antenna, radiation, because radiation comes from the electrons sloshing back and forth, the radiation comes from a current maximum. So the point on the antenna where the most electrons are sloshing back and forth right here, right now, that's your current maxima. In your sort of your traditional dipole, like we have on screen here, that's going to be in the middle. The ends, there's no current on the ends. That's an open circuit, right? Where are the electrons going to go? Volt current minimum on the ends, which means there's no radiation from these points. All your radiation is happening here in your basic dipole antenna. As those ripples, the electromagnetic radiation, as it spreads out through the universe, you can think of it like a soap bubble, expanding, expanding, expanding. As the soap bubble gets twice as wide, the surface area is 4 times bigger. Similarly with radio waves, as your waves spread out, as the distance doubles, the amount of power in a given wave cuts by a quarter. So double the distance, power goes down by a quarter. That is the inverse square law. We measure those power levels generally with decibels. We talk about, and decibels are a relative measurement. We use decibels to compare two power levels. So there's no such thing as like 7 dB of power. That doesn't mean anything. 7 dB of power relative to what? And decibels, it's a logarithmic measurement. If you're not accustomed to that, it can take some getting used to, but working with decibels does make the math a lot easier. And if you're new to it, you may just have to trust me on that for a while. Spend some time with it. It makes a lot of your calculations and understanding what's happening so much easier. But in a nutshell, 10 plus 10 dB means 10 times the power. Minus 10 dB means 1/10 the power. Plus 3 dB, double the power. Minus 3 dB, half the power. And spend some time with this and learn the pattern, and you'll get there. It does eventually make sense, and it is so helpful. In part because using decibels gives you the ability to talk about really small values and really big values in the same conversation. So we can talk about negative 120 dB and plus 60 dB without getting lost in numbers. Whereas if we're talking about, oh, you know, that's 15 million times power difference, like you'll get lost doing those conversions so fast. So we use decibels. Okay. So in talking about power measurements, we use decibels to describe gain as well, gain and loss. When in a textbook, you'll read about an isotropic radiator, and a lot of antennas will be compared to an isotropic radiator, and it's important to remember that that's a theoretical construct. There is no such thing as an isotropic radiator. You cannot build one. You cannot buy one from ham radio outlet. It is simply a theoretical convenience. That theoretical isotropic radiator, all of the RF energy that it sends out into the universe, those ripples that it creates, go out in a big sphere in all directions. Well, we can't actually build that. We can build something that's kind of close, and that's a dipole. Your most basic antenna that we all start out with buying and building, dipole antenna. And instead of sending out a sphere of energy, you kind of get this donut shape because there's no radiation coming off the ends, coming off the tips. But you are sending all this energy out this way. It all spreads out in this plane, plus or minus a little bit, and absolutely none going up and going down. So we can imagine, instead of a sphere in all directions, like our isotropic, we remove the energy that goes that way, and that gives us a little bit more coming out the sides. So a dipole, when we talk about a dipole having, what is it, 2.51 dB of gain? If I've lost Jeff, I'm in trouble. Okay. So how are we doing so far? You got a donut for me. Okay.
I was just going to show the pattern of radiation.
Yep.
Which is now being directed in one direction.
Okay, so we have a real-world dipole antenna. It's not sending radiation out in all directions in a sphere. It's only sending it out to the sides, but all the way around. So let's talk about pattern. Because we have nothing going up, we can represent that here. In our elevation, this diagram is how we represent where the energy is going from a given antenna. We have two views here. Looking down on it, with our radiation going out the sides, that's our azimuth view, this one here. And you see it's just a circle, right? We have equal amounts of energy going out in all directions when we look at it this way, azimuth. And azimuth is like a compass bearing, right? Our other view is elevation. If we're looking at it this way, where's our radiation going? Well, here, see how it comes down to 0? Up top and down below. There's no radiation going this way. we have everything going out to both sides. And then as our angle comes up, 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 we get less and less and less, gradually coming to 0 here. So that's what this is representing. And one thing to point out, if you can read the scale here, we have this 0 line on the grid, on this round grid. We have this 0 line. That is 0 dBi. So if we were to plot an isotropic antenna on here, you would see this red right here on this 0. Right here on this 0. 0 dBi means no gain compared to an isotropic. Well, this dipole that we've drawn here is actually a little bit past the 0 in this direction and in our azimuth in all directions, because the radiation that we have taken out, right? The isotropic would have radiated in a sphere. Well, we have removed what would go straight up and down, and it has been redirected everywhere else. So that's our little balloon here. This can help us understand. As we remove the radiation at the top and bottom, everything else gets a little bit bigger. The balloon gets a little bit fatter. See, we get a little bit fatter. And that's our 2.15, whatever it is, 2 and a bit dB of gain over an isotropic. We can get even more. If you, this is a plot of a collinear antenna, and the collinear is basically you take 2 dipoles, right? This is one dipole. You take 2 dipoles, and so instead of just having the one, you take multiple dipoles and you stack them on top of each other. And you feed them in such a way that they're all radiating the same thing at the same time. Asterisk, there's little ways you can tweak that to get different patterns, but in the most simplest version of a collinear, you have all these stacked dipoles, and they're all sending out the same information at the same time. And as those ripples from each antenna spreads out through the universe, you have the ripples from this one, the ripples from this one, the ripples from this one. They'll combine, and in this flat direction, they'll add together, and you'll get more signal going straight out towards the horizon. But in all these other directions, they'll add together in such a way that the trough from one, right, these ripples, right, as this antenna sends out a trough, this one or low point, this one sends out a high point, and those cancel out to be nothing in this angle. So collinears give us even more gain out towards the horizon, but not sending anything down to the worms or the clouds, where probably there's nobody walking around with a handheld to hear them. And I don't know if you noticed, if you're paying a lot of attention, our scale here, our scale changed. We no longer have 0 dBi here. That's something to pay attention to when you're comparing plots. Sometimes they can do this to be tricky. Sometimes it's just different people made the plots and they have different preferences, or they're trying to tell a different story. That's important. Our scale changed from this plot to the previous one, and that can make it look like there's a lot more gain here than there really is. So pay attention to those little numbers in the background, because this actually exaggerates the pattern a little bit if you're visually comparing it to that one. And then another pattern we want to look at is a Yagi, or other beam directional antenna. So with a collinear, we took 2 dipoles and we stacked them end to end. Here we have one dipole that has the cable coming to it. This is our driven element. This by itself is just a dipole. But we've thrown all these other wires in here to do what? These will excite sympathetically. This slightly longer one, very close, acts as a reflector. It's like putting a mirror behind a light bulb. And then all these are directors. They will get excited, re-radiate, and those waves will all interact with the original radiation from the dipole in such a way that it focuses. So we have a reflector, like a mirror behind a light bulb, and a series of lenses. And that's going to take our donut of radiation, right? So we had our isotropic, then we had our dipole, and now we have, hopefully this doesn't pop in my face. Now we have a Yagi. And at no point have we amplified. We have not turned a knob. We have not given this more power. All we have done is taken the same power we originally had and shaped how those waves spread out through the universe. And that is how we get antenna gain. And again, pay attention to your scale on these drawings. The story that this author was trying to tell was about this main lobe, and they changed the scale in such a way that your back lobe looks a lot smaller than it really is. This back lobe is like 20 dB down, which is quite good, but if you just casually glance at that, that might look like 60 or 70 down. It is not. And I just used a word, back lobe, side lobe, null. I want to go into all those real quickly. This is your main lobe, right? This is where most of your radiation is going. This is the one you want to see. This is what you're designing for usually. You get a bunch of gain in this direction. But because it's hard to design a perfect antenna, what does that even mean? You're usually going to get some radiation off in directions you don't really care about, even with our collinear that we built here. Again, there aren't any worms walking around with a walkie-talkie. Probably people in airplanes we're not trying to talk to. We don't care about them. We're trying to, if this is like a repeater site, we're sending signal out to the horizon. We want to be catching people walking around on the ground or in their car. So these lobes, so we care about these main lobes. We still get some smaller side lobes here. They're a little bit unavoidable. Same thing with the Yagi. Yes, sir.
Back on your other slide, I've got a mic, Jeff, if Mark can turn it up. You pointed out the worms aren't going to be carrying radios.
Right.
You're talking to airplanes, but what if you're trying to talk to the International Space Station?
Okay.
This antenna is not going to be very good for you, is it? And we're going to get into this a little later of putting that main lobe that Chris is showing you where you need it to be to talk to the thing that you're trying to talk to. That might be if you're, now a lot of people aren't going to be doing Earth, Moon, Earth, EME, but if you are, you want to put your signal on the moon and you don't want to listen to noisy things behind you because you've got very sensitive receivers. We'll get into that, and you might make some further comment to that as you're going through. These are great pictorials, so pay attention to this.
Yeah, so to sort of marry a few things together real quick, Willem started out, there are all sorts of ways to get directionality, yep. One of the things Willem said early on is there's no such thing as a perfect antenna. So when we're choosing an antenna to build or buy, we have to think about what problems we are trying to solve. And one of those problems is, who do we want to talk to? If we're building a repeater site, we probably want to talk to people who are on our horizon, on or near. If we're walking around with a walkie-talkie, well, we might be on a roof, we might be down in a valley. We want to be talking to as many directions as we can, usually. So we're going to be looking at something that's closer to a dipole radiation pattern. Something like a collinear if you're trying to cover horizon to horizon. Or if you want to shoot a signal up to the space station as it's going by, or you've got a tower 20 miles away that you need to get a really strong signal to, that's when you might look at something directional, like this Yagi, like this microwave dish. But yeah, just because I did use a term, I want to go back and define it. So we've got our main lobe. This is what we're focused on when we're designing, building, aiming, all that. We have these side lobes that will receive and transmit some signal. We have nulls, these little deep spots here. No signal is going to get in or out in those directions. And then another term that you might encounter is front to back ratio. And that is the relative gain between where you're aimed and who's behind you. And so these nulls, these side lobes, all of these can be useful. If you've got two guys who are kind of close to each other, one of them you want to talk to and the other one's being annoying and you don't want to hear him, you can aim it so that your annoying guy is in one of these nulls, and the guy you want to talk to well, maybe he has to be on a side lobe, but you look at like the relative difference in those signals, that's a good 25 dB of signal strength from here, from this bearing to this bearing. That can be really valuable. Even if, if you aim the main lobe at the guy you want to talk to, well, the annoying guy might only be 7 dB down. Whereas if we aim the side lobe, we can get that annoying guy way, way down here on one of these nulls. So all of this can be useful. And remember that this is a 3D plot. We've got elevation here, and azimuth here. So we're looking at one slice on each plane. This word impedance. So I'm going to go back to my dipole here. I mentioned that on the dipole, when we feed it in the center, there's this current maximum here. All of your electrons flowing back and forth in your dipole, right? As it gets sloshing back and forth, if everybody can see this, is this showing up on the camera, Dean? Tristan, okay. So we've got this little bottle of water to sort of represent our dipole that's getting fed with the signal. So like the water sloshes back and forth in this bottle, we have electrons sloshing back and forth in our antenna. So think about the different points on this antenna, the different places in this bottle. Here in the middle, you've got a lot of water sloshing back and forth past you as it goes back and forth. That's a current maximum. You have a lot of water going back and forth this spot. At the ends, well, theoretically, there's a water molecule on each end of this thing that never moves, right? There's no current on the ends. There's nowhere for the current to go. So, but we do have a lot of voltage, right? So voltage is how many electrons are piled up in this spot right now, at this moment. How much water is at this spot right now? How much water is at this spot right now? A lot of water? Not a lot. We have a very big negative amount of water here, right? So when we take those measurements, we measure our current at a given spot, we measure our voltage at a given spot. The ratio of those, voltage divided by current, that's our impedance. And impedance will become very important when we're feeding an antenna. In the middle of a dipole, the ratio, like a resonant dipole, the ratio of voltage to current at that point is about 72. 72 what? 72 ohms. It's volts divided by amps. Gives you ohms. That ratio right here, 72. You go down to the end. Well, you don't have any current at the end, right? Remember that molecule of water at the end that never moves? There's no current at the end. But you do have a lot of voltage. So if you take voltage, a big number, and you divide it by current, a small number, you get a big number, high impedance. So there's high impedance at the ends, low impedance, about 72 ohms in the middle, high impedance again at the ends, several thousand ohms. And that becomes important when we go to feed this. You take your dipole and you just solder some coax to it. Honestly, that works pretty well. Your coax is probably 50 or 75 ohms characteristic impedance. We'll come back to that in a second. And you take that 50 or 75 and you connect it to 72, well, those numbers are pretty close to each other and everything's going to be happy. So characteristic impedance, this term that I used, that is for a transmission line, its characteristic impedance is, and this gets a little bit circular, but its characteristic impedance is, that tells you the impedance it wants to connect at the antenna at. This cable is happiest if it's feeding a device at or near, in this case, 50 ohms. And 72 ohms on the antenna, close enough. But, so this is, electrically, this is easy. We can take our coax, we can solder it to our 2 wires, our resonant dipole. Everything's pretty happy. Great. But sometimes, mechanically, this might not be convenient to build. If this dipole is 80 feet tall, and you're feeding it in the middle with some coax, well, electrically that works, but can you hold coax in the air at 40 feet? That may be a challenge. So for various reasons, sometimes we'll want to feed coax, we'll want to feed our dipole somewhere else. So like a Ribicoff antenna, we want to feed it closer to the ground, for example. Well, the problem is we have really high impedance down towards that voltage maximum. And that's not going to make our cable very happy. So that big mismatch between the 50 ohms of the cable and the thousands of ohms of the antenna at that point, because at that point there's a lot of voltage and not very much current. So that ratio is up in the thousands of ohms. That very bad mismatch is going to result in a reflection. The power cannot easily get out of the cable into the antenna. And at the point of that mismatch, you're going to get power reflected back down the cable. And because coax is unfortunately lossy, it just has resistance at RF. We will end up losing a lot of our power to making the cable warmer. And we don't want that. You could also get your transmitter shutting down as all that power goes down the cable, hits the antenna, can't get out, so it comes back. As it comes back and hits the transmitter, your transmitter may shut down or turn its power output down or whatever just to protect itself. And the ways that we deal with that is we build a transformer. We put a transformer in the circuit between the coax cable and the antenna. And this is a way to take our low impedance cable and our high impedance antenna and get them moving power back and forth between each other in an efficient way that makes everything happy. And so transformer, here's an impedance transformer, right? Electrically, your impedance is the ratio of your voltage and your current. Mechanically, it can be, so you got me, a guy chasing me around the room now. We have our lever, we trade distance for force. I can pick up something very heavy by putting a little bit of force over a lot of distance. And my lever transforms that into a lot of force over a little distance. In your car, the same motor can take you from a stop up a steep hill at low speed, or can cruise up that hill at 70 miles an hour. But you need the transmission to get you in a different gear, to trade speed for torque. So our transformer is doing something very simple. For the same amount of power, we are trading back and forth between voltage and current. So we have this low impedance, low voltage, higher current on one side, goes to the transformer, into higher voltage, lower current, so that everything is seeing the impedance that it wants. Resonance, I'm going to say mostly don't worry about resonance. Resonant antennas are very easy to build, they're very easy to understand, and they become the basis for everything else we're going to talk about. All of these textbooks here will talk about resonant antennas a lot because they are so easy to understand and they are easy to build. You may build a resonant antenna. There's no reason not to, but resonance is not the same as efficiency or good performance. And there are plenty of non-resonant antennas that work really great. So that's mostly we're going to leave things with resonance. And yeah, last thing I want to cover is polarization. I'm doing disservice to all of these topics because there's so much, but we're gonna hit polarization really quick. We talked about as one antenna transmits, it sends ripples out into the universe, and then another antenna somewhere else gets those, and the electrons in that antenna start wiggling back and forth in sympathy. Well, when they're in the same orientation, that works really well. But this antenna is making the electrons wiggle this way, and so the waves are going to wiggle in that axis, in that plane. This works. But if I turn this one, these ripples can't get these electrons moving in this direction. There's nowhere to go. They just don't have, these electrons want to wiggle this way. So you're going to have this cross polarization. You're going to lose a lot of sensitivity, and there's transitions between. So if you're off by about 45 degrees, you lose about half your power just from being slightly cross-polarized. If you're 90 degrees off, you're completely cross-polarized, very, very little is going to get in. Not none, but very little. You're down about 20 dB from being fully cross-polarized. And does anybody know off the top of their head what 20 dB is in percent? 1%. So you're just from turning your radio, just from turning your antenna like this, you're going to receive 1% of the power you could have if you were like this. And that's on top of whatever you've lost through just distance, free space path loss. This matters a lot with VHF, line of sight communications, handhelds, car antennas, that kind of thing. It matters a bit less at HF because once the signal bounces off the ionosphere and the ground and back a few times, that polarization gets kind of randomized. So it's less of an issue at HF most of the time, but if you're doing anything line of sight, this will absolutely matter, including talking to the space station. Polarization matters a lot, talking to satellites. Okay, that is it for my theory slides. There's so much more, and I'm kind of going to leave it there unless somebody has a question or wants me to clarify something.
I was going to clarify something, but take the questions.
I'm realizing I didn't talk about SWR. I'm going to leave that for someone else.
Okay. What I was going to add to this is Chris did a very good job, but why is it 20 dB? And on a satellite dish, vertical to horizontal, it's much more than 20 dB.
Okay.
Why in ham radio and the frequencies we use? Because as this wave propagates, it bounces off things. That thing could be the ionosphere, it could be a building, it could be cars, and the polarization will tend to rotate, and it blurs. You do get a net of about 20 dB from polarization mismatch, which means if you're running a FM signal, we typically put vertical polarization. Single sideband tends to be horizontal polarization on VHF bands. Why did we do that? Why do we run horizontal? On single sideband and CW where you're running weaker modes or even digital, man-made noise tends to be vertically polarized. And we get lower noise horizontal. So why did we go to that in our car? Because it's really tough to mount a horizontally polarized. Do you want this sticking out the top of your car? No, so we run a vertical, so hence why these things in practice tend to be vertical versus horizontal. Somebody brought this nice little, I call this a clover leaf, but this is a horizontal omnidirectional antenna for 400 megahertz. Who brought this? Chris, great little antenna. But we don't want to run around with this on our car when we're trying to get to the local repeater. So kind of the difference between why these are and, but as a signal goes through the atmosphere, like if you're running Earth, Moon, Earth, it'll tend to rotate. It's conceivable you're transmitting to the moon on horizontal and it's being received on vertical. So the really big stations have both polarizations. So, but yeah, these are great slides. Got to have some questions for Chris before you listen to my boring stuff.
They can just ask the question.
And if they're on Zoom, you have all the lines unmuted, so we could say, this is Dr. Ruth, you're on the air.
Very cool. All right, Tristan had something.
Yeah, you want to talk about circular polarization?
Yeah, so circular polarization, actually, I can do this with these two Yagis I have here. We're going to
I
simplify
want to see
things
you
a
do
little
it with
bit.
your bottle of
Yeah?
water.
Catch.
That's kind of circular.
Okay, so vertical polarization, horizontal polarization. If we feed these two slightly out of phase, we didn't talk about feeding out of phase. We'll get there. I'm sure somebody's going to talk
Yeah,
about it.
we'll touch on that.
If we feed these slightly out of phase, we give them one gets a very slightly delayed signal relative to the other. And we kind of interleave these two antennas. Well, we have now the effect of this is instead of just having the electrons wiggling up and down, it looks very much like our electrons are corkscrewing through space as the waves travel. And that does a number of things for us. One, it means if we are mismatched, we're never more than 3 dB down from a polarity mismatch, right? Because as we have stuff in this plane, we have stuff in this plane. As we rotate between them, we lose one, losing one, but we're gaining the other. And we hit this 3 dB crossover where we start to pick the other one up. So if we are cross-polarized, we have a compromised polarization that works pretty well for everybody. You're going to be 50% down on your power from what you theoretically could if your polarization matched, if you were both vertical, but 3 dB is fine in most cases. It also means that, you talked about a satellite. If you're trying to talk to a satellite, well, those move through space. So your polarization of you with your Yagi pointed up and down, aimed at a satellite, well, that satellite could be tumbling in any direction. Even if it's not tumbling, as it goes from one horizon to the next, that can very much look to you on the ground like its polarization is changing. So circular polarization
And the
lets you hit all of
atmosphere
those.
will naturally spin.
So I'm not a satellite guy. So.
But I never thought about this, but what if you're running left-hand circular polarization, I'm
Oh,
running
goodness.
right-hand?
Okay. You have the floor.
Yeah, no, I think, Willem, what would that be, a graduate level course? But you'll find as you're looking at antennas at a flea market, you'll see actually both polarizations on one boom, typically. I guess you can do separate stacks, but that's going to be circular. You're probably going to use that for satellite or EME if you really want a big station. When I was doing Earth, Moon, Earth, I just had horizontally polarized Yagis because I wanted to take the same antenna, aim it at the horizon so I could work somebody 1,000 miles away on 2 meters, but also elevate it up and work off the moon. And I didn't want to have a second antenna because I've got a picture of one of those stacks of antennas. It's not easy to put up. So, but so good point on circular.
Okay. Well, I think.
Are we going into doublets or are we going to mine?
I think it's somebody else's turn to talk for a little
Okay,
while.
so I'll start. Well, you take some more questions. I'll work the slides. And I think it's this one.
You want to talk about your stack of books up here?
Yeah. We've got a lot of show and tell up here today. There's very little new under the sun. InFEDs are very popular right now. InFEDs have been around since the beginning, right? There's lots of great old books out there. Gosh, I don't know. What do you want me to say, Willem?